All right, so today we continue our journey with the differential equations, and today it says here differential equations of the form dy dx is equal to a function of y. So in other words, it is when the derivative dy dx, the function for that is in terms of the dependent variable y. Okay, so when we're solving these, we've got to end up with an equation of y equals. But before we can do that, there's a technique that we need to apply. So let me turn my pen on. So if dy dx is equal to a function of y. Now, if we tried to anti-differentiate this with respect to x, the left-hand side there would be no problem at all. However, the right-hand side is a problem because the function's in terms of y, not in terms of x. So the technique that we need to do is this. So then what we do is we flip this over and we say, okay, dx dy, whoops, not dx dx, dx dy, dx dy would be equal to, now we're going to flip this one over, so if we pretend and think of that as f function of y over 1, it's 1 over our function in terms of y. And now we can differentiate each side here with respect to y. And so if we do the right hand side, dx dy dy, the dy is cancelling, leaving us with integral of dx, which is just x. And the right hand side here is the integral of 1 on the function of y dy, which doesn't simplify, and so what we're looking for is the integral of 1 on the function of y dy. All right, and so then we do our antiderivative, and then after that, because we're wanting our final answer to be y equals, as y is our dependent variable, we need to go y equals, because the dependent variable has got to be the one that's equals. All right, so we then rearrange, and we'll do a couple of examples here where I'll show you how we go about that. All right, so here we go, find the general solution. So if we've got something here that says general solution, that means we're going to have plus some constant in there somewhere. All right, and we'll deal with that when we deal with that. We've got y greater than negative a half. All right, so if y is greater than negative a half, we don't need to worry too much about that now, but later on we're going to use that. So if y is greater than negative a half, then if we put y is negative a half in there, you'll find that then the derivative here is going to be greater than 0. But anyway, I'm getting ahead of ourselves. All right, so we've got dy dx equals 2y plus 1. And now we need to deal with that so we can anti-differentiate. So what we do first of all, as I indicated before, we flip both sides. So dx becomes dy. The left-hand side becomes dx on dy, I should be saying. And here, if we're thinking of that as over 1, it's 1 over 2y plus 1. All right, so now we anti-differentiate that, both sides, with respect to y, and of course we already know that the left-hand side is just going to become x, so we can jump straight to that. And the right-hand side is 1 over 2y plus 1 with respect to y. All right, so now we have quite a number of different strategies here that we can use to anti-differentiate here. So 1 over, well, there's no squared in there, so it's not going to be an inverse or inverse circular function, so it's going to be some other thing. So what can we do? 1 over does kind of indicate maybe a log, so okay, so maybe that's a log. So let's have a look. Then we need to do a substitution, and so let's let 2y plus 1 equal u, and I've written that backwards, let me write it the other way around. So let's let u equal 2y plus 1. If I then du dy, because if I'm going to replace that with a u, then I need to replace my thing I'm differentiating with respect to, or anti-differentiating with respect to in this case. Got to change that to in terms of u, and of course when we differentiate that we get 2. And doing a bit of rearranging, dividing by 2 and multiplying by dy, you get that dy would be equal to du over 2. So let's make those substitutions. U there, so dy is du over 2. This over 2 here, we can bring that out as a factor of a half at the front, 1 on u du. Alright, so let's have a look. So then that would be a half, 1 on u, the antiderivative is log to the base e of u, and then plus c. So that's what it said, the general solution. And so that's what I said earlier, there's going to be a plus c in there somewhere, and here it is. All right, so let's substitute back then, and so x is equal to a half log to the base e of the magnitude of 2y plus 1 plus c. Now you remember we had a restriction for y, and y was greater than negative a half. So if y is greater than negative a half, then 2y plus 1 will be greater than 0. And given that that is the case, these absolute value signs are, in this case, not necessary. So we can leave them out, and we can just write 2y plus 1. So in this case, we can leave them out because we know that what's inside here is going to be greater than 0. And remember, of course, you can't take the log of 0 or a negative. Okay, so now we've got that, and now this is our independent variable x, and our dependent variable is y. So we need to rearrange that equation to get y equals. Okay, let's take c. Get rid of this half by multiplying both sides by 2. So then we have 2 x minus c equals log to the base e of 2y plus 1. And we need to get rid of that log to the base e. So to get rid of a log to the base e, we do e to the power of. We're getting there. Take 1. So e to the 2x minus c, take 1 is 2y, and then divide by 2. Now dividing by 2, we often would see that written as a half times. And there's our y. All right. So there's our function general, because it's got a constant in here. and so that's y equals a half e to the 2x minus c minus 1. Now, sometimes what you'll see is they'll fiddle around with this stuff here. And so what they'll do is they'll fiddle around with that stuff there and say, okay, that's the same as a half e to the 2x minus 2c minus 1. And this bit here, if we use index law in reverse, the first one, we can go that that's e to the 2x times e to the minus 2c minus 1. Now, this bit, the e to the minus 2c, because remember, c is a number, a constant, a number, so negative 2 times a number. So it's e, which is a number, to the power of a number. So if you have a number to the power of another number, you get a number. Call it a. So sometimes you might see this answer written as a half a e to the 2x minus 1, where a takes into account that constant that we had up here all the way back to there. So this c here is wrapped up into this. Shouldn't have that. I made a bit of error there. It's negative 2c, not negative 2x. C to the negative 2c is equal to a, this one there. Sorry if I've confused anyone. All right, so this a has that all wrapped up in it. So a is a number, a constant, because this here is. All right, so sometimes you'll see it like that. Which one's better? I don't know. The last one that looks a bit neater, I guess, but it's the same kind of thing. If you've got $10, is it better to have it in a $10 note, or is it 20, 50-cent coins? In the end, you can buy $10 worth of stuff with both, but it's easier to carry around the $10 note. So I mean, this looks a bit easier, a little bit neater, but both of those are answers. All right, so starting to waffle a bit there, so let's get on to the next one. All right, the next one, there's a bit of fun stuff that's going to go on here in this next one. All right, so dy dx is equal to 1 minus y squared, and then we've got a restriction on our y. It's got to be between negative 1 and 1, and we'll probably use that later. All right, so again, dy dx, so, and it's, we'll think that's over 1, so flip both sides, dx dy is 1 on 1 minus y squared. Now anti-differentiate both sides with respect to y. We can go straight to x, and now we've got 1 on 1 minus y squared dy. All right. So now we kind of have a look and think, what does this relate to? Inverse circular functions. Oh, it's not quite the tan one, is it? Because the tan one has a plus here. All right, so we've got to do something else. Now, what else can we do? All right, if you notice the bottom here is a difference of perfect squares. So it's 1 minus y times 1 plus y dy. So what we've got to do is we've got to do something with this. And the something we've got to do with this is partial fractions. So I've got another page here I'm going to look at. So I know that when I go back, I had 1 on 1 minus y squared, and I know that's the same as, equivalent to 1 over 1 minus y, 1 plus y. All right, and so now I'm going to do partial fractions there with that. And so if I do for partial fractions, splitting them up, I have 1 minus y here, 1 plus y here, and I have a there and b there. All right, let's make these look more like each other now. So common denominator. And simply multiply those things together. All right, for the left-hand one, the 1 minus y was there, so we had to do the top by the 1 plus y. Over on the left-hand fraction, the 1 plus y was there, so we have to multiply by the 1 minus y. All right, put it all over that one denominator. And then we've got a1 plus y plus b times 1 minus y. Okay, so if these things are equivalent, and we already know that our denominators are the same, what that means is that then our numerators must be the same. So if our numerators must be the same, then 1 must be the same as a times 1 plus y plus b times 1 minus y. All right, so there's a couple of different ways we can go about it. We could expand, collect like terms, come up with simultaneous equations. Or what we can do is we can have a look at these brackets that are here. And we can say to ourselves, okay, this one here, if y was minus 1, then you'd have 1 plus negative 1, which would be 0. So when y equals minus 1, what we would have, this one over there stays the same. But here we'd have a times 0 plus b times 1 minus negative 1, which of course is 2. And so we would have that 1 would be equal to 2b, so b would be a half. And then if we do a similar thing and we have a look here and we say, okay, well, if y is 1, then this bracket becomes 0. So when y equals 1, we'll have 1 equals a times 1 plus 1 plus b times 1 minus 1, which of course is 0. So we'll have 1 equals 2a, and so a is a half as well. All right. So how do we then put that? So we've got this. So if that's a half, and b is a half, we'd go 1 half. B is a half, we go 1 half. Like so. So then what we have is then we have 1 over 2 1 minus y plus 1 over 2 1 plus y. Oops, 1 plus y. All right, so I'm going to take that there and I'm going to put on my previous page there, I'm going to put that on here. So that's what this now becomes. So this now becomes the integral of 1 over 2 1 minus y plus 1 over 2 1 plus y, dy. Now, of course, there's a factor of a half in each of those, so we can take it out the front. The integral of 1 over 1 minus y plus 1 over 1 plus y dy. And so now, like in the previous example, this is looking like we've got logs. So, which of course we have. So when I anti-differentiate this one over here, plus log to the base e of the magnitude of 1 plus y. And over here, log to the base e of the magnitude of 1 minus y. Plus our constant on the end, that's the general solution. Now here, excuse me, here, when we differentiate 1 minus y, we get a negative. Now, there's no negative up there, so what we do is we have one in here. So a negative appears here now because of that. All right, so we could go and you can let u equal and all that sort of business. And here's what we end up with. All right, so now if I rewrite this in another, the other thing too, this restriction here. So remember, -1 was less than y was less than 1. So if y is between those, then 1 minus y and 1 plus y are going to fit. They're going to be between 0 and 1. You can test that out if you like. So I don't need our modulus signs. So I've still got my half. So if I write this as log to the base e, I'm going to just change the order of 1 plus y minus log to the base e of 1 minus y. You'll notice here I'm subtracting logs. Now, when I'm subtracting logs, I would divide these things. So I've got 1 plus y over 1 minus y plus some constant on the end, and that's x is equal to that. All right. Now, here we go. We've got this here. Now, I've got y's here in 2 places. Right, that's a bit of a problem. But first of all, I can get rid of this c and I can get rid of this half. So if I take c from both sides, log to the base e. Now I don't need 2 brackets, I can have one bracket. Then if I times both sides by 2, I've got that. And now, need to get rid of the log. I can do that, e to the power of, so it's all right. So far, e to the 2x minus c equals 1 plus y over 1 minus y. Okay, so the issue we've got, and I already sort of flagged this, is that we've got y in 2 places, up the top here and down the bottom here. We need to have it in 1 place. So a technique that we can use to do that is, first of all, let's get rid of this denominator, this fraction. And so we can do that by multiplying both sides by 1 minus y. So if we do that, we do 1 minus y times e to the power of 2x minus c. And on the right hand side, it's just 1 plus y. All right, so next we go, okay, so I can expand this. So if I expand that, 1 times that, so I've got e to the 2x minus c minus y times e to the 2x minus c equals 1 plus y. And we go, okay, well, that's got a y in it. That's got a y in it. But these other bits haven't. So let's get the bits that haven't got the y in them on to the left, and the bits that have got the y in them to the right. Okay, so alright, so e to the 2 power x minus c. It's already there. Got to move that 1 across, so I've got to take 1. This y is already there. Got to move this across here. It's minus, so I've got to add. And then we go, oh, hang on. Well, now we've got y here as a common factor. So I can take that out. Take that out. Guess what? We've now only got one y in there. Beautiful, because that's what we want. All right, now in here, of course, is times. Opposites of times is divide. So if we divide both sides by that whole fraction, you'll get that y equals e to the 2x minus c minus 1 over e to the 2x minus c plus 1. All right, and so there is a general solution. You could fiddle around with these things here. All right, just like I did in the previous example, to change that to get an A if you like. But just be aware that this is a general solution. May not be the neatest looking one, but it is. And this C here and that C there, they're the same number. Right? If they weren't the same number, then they'd be different letters. Okay, and that's it for that exercise. So you've seen the techniques that we use and the strategy that we implement there. You've seen another strategy here down this last bit. If we got y equal and we've got y in 2 places to somehow get it together. All right, so if you need assistance with any of that stuff, make sure you ask for it. And as always, have fun.